Hello, welcome to today's class. Today we will talk about convolutional neural networks. So last time we talked about some of the main components of the deep neural net. So in this class we require you already know some of the basics of the deep neural net, also the convolutional neural net. I actually briefly went over some of the main components of the deep neural net. What are actually their main concept and something like that. And then today we will review the basics of the convolutional neural net, which is CNNs, which are actually very commonly used for the many these computer vision related actually the tasks. So the convolutional neural net, the CNNs are one of very common deep neural net. Actually, the main reason why we are talking about the CNN is that it can provide different levels of features. It can provide low level features, also very high level semantic the features. So that actually we can use those features for the image search or also many other computer vision related tasks. And we already know that actually this CNN has been achieved the very good results across many different actually computer vision related problems. Here I showed some of the early on this CNN architecture, this RxNet. So at the end of this, I mean some of you fellow students mentioned that they don't know the meaning of stride or something like that. So we cannot talk about all the low-level details here, but I wish that at the end of this class you can actually understand that what this diagram means and what this term means. So we are mainly working with the images, right? And then for image search, we need some features, right? So before we talked about SIFT, right? We actually had a different tasks for extracting features, but basically we wanted to extract the selective and also invariant features, right? Basically, selective means is that given this feature, I mean, we need to uniquely identify some part of the object, right? So the image, the path should be the interesting, also it should be the distinctive ones. So that's why it should be selective. Also, it should be the invariant, right? Invariant to the various changes like elimination change, right? And then we can just use the deep neural net to extract those features. But actually, if you look at the development of the deep neural net, also the CNN, actually some of the technology turn out to be very well for the deep neural net. Actually, borrow from the classical image processing or computer vision techniques. In other words, we wanted to exploit the knowledge of images to accelerate or also even improve the performance of our deep neural net, our CNN techniques. So instead of designing manually design the features or the technique, we in the category of in the approach of the deep learning, we obviously prefer to learn those actually different parameters, even architecture and so on. So first one is that this actually image, and then you probably remember that we use this kind of illustration, right? You can treat that this kind of each individual element of pixel value of your image, and then we can actually from here we can take the sigmoid function, and then we can get some sort of response function, right? And one simple one is that we can extract the high level feature out of all the pixels in the image, right? But if we use this approach, it might require a lot of connection here. And then for each connection, we need to actually associate some sort of the weight parameter, right? Then it means that we need to use a lot of weight, right? Obviously, we can try this one, but it turned out to be not that useful in practice. So also there are a lot of so when you talked about SIFT or Hertz corner detector, we use the concept of the window, right? It means that instead of looking at every pixel in the image, we only look at the local patch of the image, right? So based on those experience, we mainly use this kind of local connectivity. In other words, to get some sort of the feature some activation, we only look at only the partial of the image. So you can treat that as actually the local window, something like that. And then basically given this some of this local image patch, we actually make the connection to this output value, and then basically we also need this weight weight for from the this from the this local image patch, and then it actually the weight vector. If you consider all of those weight, in the end, through the deep learning, we need to compute the weight, right? But this weight actually there can be considered as some sort of the specially localized filter. So also by using this local connectivity, you can reduce down the parameter a lot compared to this approach. And then we actually here for this one we use this one activate. You can treat this kind of filter, right? We apply this kind of the weight to the image patch, and we got some result, right? And we can also we can think about it different filters for this image patch. This green window. Also, we can think about another filter, another weight for this red window, something like that, right? So we can actually think of neuron as a viewing small adjacent window, something like that, right? We can think about many different neurons like this, and then basically when you specify this neuron from this window, we can actually we can introduce concept of this receptive field. In other words, for computer output value here, actually this actually we can treat this H from this G value from the RGB value, the one, and this big W is the actual weight function. Before actually we used the sigmoid, we took the sigmoid, but actually we didn't show the sigmoid here. But to compute this activation, actually we look at the pixel within this window, right? Something like that. That's also known as this receptive field. It means that to compute the output value here, we look at this one actually. Basically, based on the result, based on the value of this the pixel in this local window, we compute this value, right? That's the definition of the receptive field. And also when you compute this output value, also we need to shift this window to there, right? And then over there we need to think about this spacing step or stride, right? For compute this one, we can shift the window 10 pixel or 20 pixels, something like that. Depending on that, actually we can get a different result. So that's known as the step and stride. You might some of your fellow students mentioned that what's the meaning of stride. Actually, that's actually the definition here. That could be the very different actually the receptive field size or also the step or stride. There could be some of the usually we need to try out different receptive field size, step or stride. Depending on that, actually we can get a different accuracy for your task, right? But actually some of recent techniques, some of the recent deep learning technique actually they try to even actually compute this kind of the values and the network design in a way that we can get achieve the best actually accuracy, best result. And then we can keep actually think about a different filter across the different so that we can cover all the image the space. And then since actually we actually apply this kind of spatial filter across filter, right? And then you can see that even if we look at the output here, also we can think about we can think about some sort of spatial information between these output one, right? So this is actually one example. We specially organize these filters, right? And as a result, output features of activation value or output feature can also be organized like image. So you can treat that. We actually take the filter here. We got some of the value here, right? But if we keep doing that across 2D image, and this also we can treat that this activation map as a 2D, like some of image, right? And here XY dimension also along this actually 1D example. You can treat this 1D the value. You can think that it's one row of the image. And then given this one, we actually we filter one thing and we got one activation. The left window, the next window, we got another one, right? You can actually treat that. Also, we have here in this case we also have the 1D structure, right? And here XY dimension is corresponding to XY position of neuron of these activations. Also, we can think about it different channels. So here, for computing one activation, we use the one set of the weight, right? But also we can try it out another set of weight, right? To compute the another activation one, right? So this is actually the another activation over different channel or map. And for example, even the if you look at the RGB image, it has an RGB channel, right? And then further this also the activation, we can also use different channels. Why not, right? And then channels are kind of can be considered as different feature extract from the same special location. So we can actually use the multiple filter. For example, when we talked about Harris corner detector, actually you might recall that we used actually this second moment matrix, right? But actually we can think about some other actual matrix type like the Hessian or something like that. We can actually think about it different weighting function, something like that. So that way we can use we can extract the different output. Also, as we developed this deep learning, we actually starting from 1D, we got the one activation map, we have another activation map, and then since also we can treat it as another image, we can also stacking this approach again and again, right? So that we can keep stacking the different layers actually. Here, actually, I just mentioned that across different spatial location, we can use the different filter weight, right? But it turns out that actually it's not really necessary to use different weight. So even with the local connection, actually, we might use too many weights. In this case, when you use the varying channel across these spatial locations, also the image tends to be stationary. It means that even though there are different different patch tend to also have the similar low-level structure. For example, when you also extract this Harris corner detector, we look at second moment matrix, right? So in other words, we can actually look at the second moment matrix out of this input image, right? Also the fifth case, we use this block detector, right? It actually we use this block detector across the same image, right? So in the same way, we can use the same filter across this special domain. In other words, we can just using the same filter and again. Again and again. In other words, we use the same weight for this computing this neuron. Also use the apply same filter and weight for get this activation over there. That's actually the weight tiling, or it means it's a convolutional network. So basically, convolution is one of the very common image processing operator. I will actually talk about this convolutional approach, but here we apply the filter across the 2D image or 1D image, and then we got the result, right? That's what's known as convolution. This convolution operator. So that's why it has the name of the convolutional network. Okay, here. So far I just give the high level idea, but I'd like to give a little bit more low level detail here. So for each convolutional layer, so sometimes actually we use this example, 32 by 33. It means that the width and height is 32 by 32, and then 3 is the channel, number of channel. You can see that is RGB channel. So and then given here, we can apply this. I mentioned that the different weight. I said that this actually the filter, right? It's a 5 by 5 by 3 filter. You can see that actually there are also for filter, it means it's a different weight, and then width and height of this filter and 5 pixel. Also it might have 3 different channels, something like that. And then we convolve the filter with the image. So it means that we stride the filter across the image, and then performing actually computing kind of dot product between this weight of this filter. Also there are certain this local window of this image, right? And then we got some output value, activation value. Here we actually align this filter and this at this local window, and then we do the dot product between this image and filter, and we got some output number here actually. These are the more detailed information. This actual weight function. Also we can use some sort of bias value, which overall they creating some sort of the linear kind of this partition classification plane in the very high dimensional space defined by this feature in the space of X. And if we apply this one, this filter here, then we got another activation map, right? So that's why we can treat this one activation map as another feature, another image. And also there could be many different filters, right? We can different filters so that we can different activation map. We don't need to use we can there could be there many different filters, right? We can, as I mentioned before, we can use some filter, other filter, and so on. And then here we got we used actually 6 different filters, so we got 6 channels for the activation map. And then also once you got this the value one, also is apply the convolutional neural net. Also we can use the sigmoid function, right? If actually I talked about logistic regression, so we take then near the end of step we take the sigmoid function, right? But instead of sigmoid function, I mentioned that is the rectified unit also turn out to be better than the sigmoid. Also we can use the sigmoid function over there, and then you can keep stacking that. We actually apply this approach again and again, and then it actually it becomes very deep. So it means that the convolutional neural net approach. So the question is that, so now starting from the RGB image, we applied this convolution approach, and we got some activation, another convolution approach, and then we got another one, right? What this actually the activation map look like across different layers. So there has been some of the technique visualizing how this actual activation map looks like. You can also treat basically how the weight looks like. So here, if we visualize those, if we visualize those weights, this actually the low level that's close to the actually RGB1, and then this actually middle level feature of the high level one. High level is more far away from this original image. And if you look at the low level feature, that's a very kind of more simple. You can see that it looks like here actually they try to look like only the black and white background. So probably it can respond to very well with the sum of edge, right? And this kind of one edge change, color change. But if you see that here, it's a kind of the white black and white black, right? Basically, it also the kind of the more the high frequency information, right? And also you can see that similar kind of rotated pattern, something like that, right? But if you look at this middle level, this looks to be much more complicated, this one, right? And then if you look at the more higher one, so there seems like this network actually this actually the VGG, very deep neural network, and then one of their main task is that classification. So they wanted to classify whether this image contains a dog or not. So some of actually it's not really clear how this highlight features looks like here. But actually, if you look at some other visualization, actually some of the highlight features may be corresponding to the shape of eye or something like that. Some of very kind of parts of the animal or human being, something like that. So you can see the overall low level features more low level feature corresponding to the corner or edge, but high level feature corresponding to the more semantic concepts. That's the kind of our observations about these features across different layers. Also, there could be many different technical approach. So typically, also we use the contrast normalization. For example, actually here we have the same image but with a different contrast. But here you can see that you can see the structure more clearly, right? Mainly because that there are more. If you see that actually some of the color edge more the darker, also white. Some other one is more brighter, right? If you visualize it, the histogram of color, there could be we using the different colors a lot, right? So that actually we can see the structure better. But if we reduce down this color histogram, so in other words, mean value and max value are very close to each other, then it's very difficult to see that, right? So same thing even for the deep learning, right? So this actually you can see that it's a kind of the RGB, and then if we look at this RGB value out of here, obviously even deep learning has a difficulty to understanding, right? So typically we adopted this contrast normalization. It means that usually there could be many different approach about contrast normalization, but one simple approach is that we compute the standard deviation of this color, right? And if you divide the color value with the standard deviation, in this case standard deviation very small. Then if you divide this color value with this standard deviation, then the histogram maybe expanded something like this, right? So that way you can actually you can increase the min and max. In other words, you actually normalize this min and max value of color into the sum of the canonical space. In this case, something like this. So we can apply this kind of contrast normalization out of some value. Here actually you can subtract local means. So that actually the value could be negative or positive along the G value, and then they divided each value with the standard deviation. So we can also treat that actually at that case when you subtract the mean value out of the value, we normalize this value and then subtract the value from the mean one, then the G squared, this turn out to be actually this can be considered as a kind of standard. We can see the kind of variance of this value. And then we consider each weight, and then if we take this one, we can actually do we can apply the sum of this contrast normalization. There could be very different approach, but actually in the field, if we do this kind of approach, actually we can achieve this kind of contrast normalization. There could be many other directions, but the concept is that this concept is very common, and also this concept has been shown that it works. It improves the accuracy. You can see that easily. You can intuitively see that actually, obviously, we do the contrast. We can recognize better, right? Also the pulling. So so if you remember the shift, when you actually when you expect the shift, we look at the sum of local patch. I don't remember exact number. Say that we look at the 64 by 64 local image patch, right? And then I don't remember, but for 8 by 8 8 by 8 patch, we actually compute the local histogram, right? We compute the histogram of the gradient, right? Why 8 by 8, right? Basically, if you read the shift, actually they tried a different local image patch, right? And then they found that some of the local patch turn out some specific size of local patch works quite well, and so that's what they used. But why they used the local patch? And then you might remember that we also computed this we detect the local maximum along this spatial space, also this scale space, right? And then the local maximum, in other words, suppose actually in here we have certain kind of intrinsic key point here, right? But depending in what direction you're looking at, or also depending your location, depending on your location. Basically, this key point may be located here or there in your image, right? But out of this local patch, if we compute the average of some other one, then basically even though your key point is located here or there, and then if we average out, then somehow this intrinsic key point we can actually get some information of having that intrinsic key point at that activation level, right? So also if you look at the local maximum here, the local maximum can be located over there and there depending on your location or view direction in your image. But if we do if you only look at the local maximum, take the maximum out of this local patch, that value still, even though actually they are located here and there, but they can be captured in this activation, right? That's the main idea of the pooling. So basically, the pooling is kind of functional layer designed to represent invariant feature, right? We wanted to design the feature in invariance, the various change, right? So that's why we use we actually use the local maximum and some other technique even for the shift, right? We use the similar structure even in the convolutional neural net here, and then out of this local window, we can actually use some people say that average the pooling or the N2 non-pooling or the maximum pooling is the kind of the good. But actually that depends on your task and application. But this is also very kind of the common approach. So for example, we do the contrast normalization first, and then we do actually this kind of pooling further computing this activation map. And actually, this is one of the very well-known network architecture, AlexNet. You can see that you can now see this different number starting from the image. We got you can see that actually this receptive field, we applied convolution operator here. We got the one value at the activation map here. And here we used this straddle for max pooling, and so on. And basically this convolution neural net based on the concept of local connectivity, they use the max pooling. Also, they use the rectified linear unit instead of sigmoid function. Also, they also embed this contrast normalization. And here I didn't really talk about dance one, dance network, but actually, as you can see that this name, as you can see from its name, basically, for computing this value, we actually look at this full network. The dance one also can be considered as the fully connected layer. So further, say if you have the input is the 1 by this big vector, then we actually we consider all the connection for expecting one output. We look at all the input. So that's why actually for this case we need to have this big weight value for further extracting this 10 activation actually. And that's the fully connected layer. Also, here actually they use different name of the dance. So as you can see, even though the RSNet is kind of old now, they achieve very good result in terms of this actually the classification result. They mention that I don't know what it is, but the RSNet can even mention name its name. I don't know. Also, there has a lot of progress application of the convolutional CNN to the segmentations. So we can actually we can segment the image, pixel or the super pixels. Also, we can detect. We can actually we can apply the sum of detector across the different window. We can actually get this one. Even further, we apply this approach for the robotic grasping. So, given this image, I want to know what are the region that I have to grasp it, right? So also they apply some sort of CNN-based approach. Okay, so I talked about actually some of the main components of the convolutional neural net. I also give a little bit of information about the convolutional neural net, but I didn't really talk about a lot of the very important concepts like what are the regularizer, what are this training approach, something like that. But actually we cannot cover all the low-level details here, since I just assume. I know that in this class we assume you know some of basic the deep learning, also the convolutional neural net, and then I just talk about some of the components that also relate to our main topic, the image search, especially feature and some other ones. Okay, so before I finish off, so far I talked about some of the components of the image search. We mainly spend about we actually mainly talk about this feature, right? Initially we talked about the corner detector, Harris corner detector, and then also we talked about some of the very well-known manually created features, the shifts that are like rotation, also the scale invariant. Also, we talked about the CNN features. But here, except for CNN, I talked about deep learning. Initially, I mentioned I started with the logistic regression with each loss function, the cross entropy. We can actually stack up this logistic regression layer by layer. And then we can optimize based on the stochastic gradient descent, which is very common optimizing method. Also, actually, I moved to this convolutional neural net, and based on one, we can extract the feature, and then we set the CNN features. Okay, that's the kind of the summary of what we have talked about so far. And next time, now I'll move on to how we once we have a feature, CNN feature or the SIF feature. Then we wanted to actually we can have many we can extract many features out of one image. Now we are building up some sort of indexing scheme and searching scheme so that we can identify the similar image out of a lot of images in a very fast way. I will move on to this one, and then the regular homework. You need to come up with the question 3 times before the midterm exam. Yep, that's it. Thank you. Bye.